Is there an easier way to do this? Yes, there is. Of course, you still have to compute the effect size. And the easier way is to use the program gpower, which is a free download application. The screenshot here shows the web page. If you just Google gpower, asterisk power, you'll find it. And this is created by professors in Germany. It's widely used in social sciences, social behavioral sciences, so you can trust it. gpower can help you plan the power you need for a study, and it can provide estimates of the observed power from a study you've already run. It's got a number of different options in it, and I'll just show you a few screenshots here. If you're interested, you can go and find it, play with it. It's a very good tool. So from our data, from that t-test that I had up on the board, that we've been working from, the sample size was 16, R equals 0.47, and alpha is set at 0.05. So I plugged those values into gpower. This is just the screenshot of gpower running on my computer, and it tells me the power equals 0.509. So again, that's there's a little bit of rounding error or whatever, but essentially we had the same thing. We had the same result. So if I can get my little marker here, here's where I input the values for the sample size right here, alpha, and the effect size. With those three parameters in place, it calculates it and tells me my power was 0.51. That's the observed power of the study. More useful, perhaps, is to use gpower as an estimator to predict how many people would we need to use in order to reach power equals 0.9. Remember, power is your ability to reject the null hypothesis if it should be rejected, and we want to reject the null hypothesis in order to show that the treatment works. Well, why do a study if you're only going to have a 50% chance of success? It makes no sense. I'd rather have a 90% chance of success. So how many people do I need to get power equals 0.9? It tells me my total sample size would be 40, so 20 in each group for my t-test. And using the different options in here, you can set it up for different types of statistical tests, which have slight variations on the demands in order to reach specific power. But, just a table like this from Rosenthal and Rosnow's textbook, Essentials of Behavioral Science, this is sufficient to make predictions with. So let's say we have a small effect size that R equals 0.10, that we're anticipating in the study that we're planning that R equals 0.10, and we want to have 90% power because we want the study to work. So how many people do we need? Well, you identify the effect size in the column header, and then the power that you want is down here, 0.9. Cross-index those, and it tells you we need 1,048 people in our study in order to reach power equals 0.9. So that's a large sample size, and it's not easy to get that many people. That's why small effects are very hard to capture, and you need very large samples in order to reach significance on measurements of things that have small effect sizes. Now, I'll use the same parameters in gpower. Let's see if we get the same thing. We want power equals 0.9 with R equals 0.1. And it tells me that the required sample size would be 1,043, so virtually the same number as the table showed us. Now, moving along, let's see what low power looks like. With this situation where you have low power, the experimental group and the control group are fairly close together. Each of these distributions represents a theoretical sampling distribution, one for the control group sample and one for the experimental group sample. As you increase the sample size or decrease the sample size, that will change the width of these intervals around the theoretical sampling distribution. So if you have a small sample, these distributions get wider, and if you have a large sample, the distributions that you're looking at here, the bell curves, will get narrower. Each one of these, of course, has its corresponding region of rejection for the upper and lower tails. And within each curve, you have the sampling space within which each of your samples will be likely to occur. So when you sample for the experimental group, which is the blue curve, your sample mean can fall anywhere within the space. And when you sample for the control group, which is the sort of reddish curve, the sample mean for the control group could appear anywhere within here. And that's, of course, based on random factors. So you really don't want overlap between these. Low power is the situation where your sampling distribution for the control and experimental groups have a lot of overlap, and you don't want that. Because you have substantial overlap, it is likely that you will not get significance, that you will not see any difference between these. And using the same parameters, you can determine where is beta, and whatever's left over after identifying where beta is 1 minus beta. 1 represents the entirety of the distribution here of the second curve, and beta is based on the demarcation of the region of rejection for the control group. So anything from that region or above will result in significance, but anything below that mark in this region that I call beta, the blue shaded region, that will yield non-significant results. So we want our experimental group mean to be within this unshaded region, and that's power. 1 minus beta is power. So the blue shaded region is beta down here, and you can see that it encompasses most of the possible range for the experimental group, which is bad. And that's indicative of low power. Only sample means that are to the right of the blue shaded region will be significant. Now I'm just estimating this based on appearance, but let's say that the blue shaded region is 75% of the experimental curve, then my power is 0.25 or 25%. Meanwhile, high power looks like this. Very little overlap. And this would be the picture that you get when you have a large effect size. Having a large effect size means that the population values for the variables that you're measuring are far apart. That the treatment group population value mean and the control group population value mean are far apart. Of course, you don't know how far apart they are, so we're making estimates of these things. But this would be, this diagram illustrates what it would look like to have high power, and this, to me, it looks like about 90% high power. You identify the region that's beta, where you have overlap, and 1 minus beta would be the power of this study. What would happen if we increase the sample size in this current example? When you increase the sample size, the distribution of the sampling range gets narrower. So the theoretical sampling distribution with a larger sample size gets narrower and narrower, and when you have a very, very large effect with a large sample, you're going to have very little overlap, if any, and beta will be approximately 0. I put approximately because theoretically these tails of the distributions never touch down. But according to this diagram, it looks very close to 100% power. Of course, that never really happens in real life. This is just theoretical. But now let's return to the low power example. With our low-powered example, you have population means for the control group and experimental group that are fairly close together. And you have a lot of overlap between the probability distributions based on your sample size for the control group and the experimental group sampling area. And you can see the amount of overlap here that represents beta is quite substantial. Well, let's say we increase the sample size. With increasing both the control group and experimental group sample size, the width of these distributions becomes narrower, and you can see that the overlap here that represents beta is no longer quite as pronounced. You have a little bit more room here for 1 minus beta, a little bit more room for the experimental group to be found significantly different than the control. And looking at this by eye, I would estimate this to be about 45% power. Again, I'm not using real numbers here. These are diagrams that I created myself, and these are approximations to give you an idea what's going on. If I have extraordinarily large sample sizes, then I'm going to get a situation that looks like this, even if the effect size is small. Remember, significance equals effect size times sample size, or leveraged by sample size. So if you have a small effect size, you need a very large sample in order to have decent power and detect that effect. So you can see here what happens. The sampling distribution becomes extremely narrow, and in this diagram it looks like there's only about 5% overlap in that shaded region over here. The blue shaded region for beta is very, very small, and 1 minus that area gives us power. So the main points shown here are that power mostly depends on these two things. There are some other things that influence power, but the two primary things that influence power for any study is the magnitude of the effect size, which is the difference between the means of the different populations that you're using, and the sample size, which influences the width of the curves of your probability distributions. And of course, it's a lot easier to change the sample size than it is to change the effectiveness of your treatment. I suppose if you were using a drug treatment, you can just add more drugs. But that's often not practical, and if it's a medical situation, it may not be appropriate. But sample size, you can always get more sample. So, honestly, I don't understand why people do studies with small samples. They're just sort of shooting themselves in the foot in terms of being able to get significance. Large samples are always better because large samples give you a more precise estimate of those true population values. So I hope that helps with your understanding of the relationships between power, effect size, and sample size. And I'll be doing some more tutorials similar to this on related issues in the future, so watch out for those. Thanks for watching.